Last lesson we talked about rates of change, and recall that rates of change are simply gradients. Okay, so we can have a positive rate of change, that's a positive gradient. We can have a negative rate of change, that's a negative gradient. We can have a zero rate of change, which is zero gradient. What we're going to do today is to talk a little bit more about the constant rate of change. So here we've got a car travels from Copenhagen to Charlegum, which is a distance of 150k in 2 hours or 120 minutes. Assuming the car travels at a constant speed, draw a distance time graph and calculate the speed. All right, let's do it. So we've got the vertical, the horizontal, and we've got the time, which goes on the x-axis, and distance, which goes on the y-axis. So at time zero, no distance has been covered, and 2 hours later, or when t equals 120, we've done 150k. So we've got that point there. Let's just draw our line connecting the 2 points. Okay, and there's our graph there. Now, what we want to do is calculate the speed. Okay, so the speed is a rate, right? And what it is a measure of the distance covered in the time allotted. Okay, so distance over time. So you might have seen that formula in Year 10 physics or something like that. Speed equals distance over time. All we're doing. So to calculate the speed of something, what they do is they look at a particular distance covered and the time it took to do that distance. That's what a police officer did to me as I was going down, which road was it? Somewhere in Glen Waverley, and it was a 50km/h zone. I actually got a speeding ticket, unfortunately, girls, for going 55 kilometers an hour in a 50 zone. Okay, and that's because what they were doing was measuring the distance I covered in a particular amount of time, and found that the speed at that time was 55 kilometers an hour. So I was, I don't know, I think it was about $200 in my pocket lighter, and also incurred the wrath of my wife, which was much worse. All right, so onto this particular scenario here. So what we can do is the distance over time. So the distance covered was 150 kilometers over the time covered, which was 2 hours or 120 minutes. So that is 75 kilometers an hour. And note that on this graph here, I can get that by working out the gradient of this line between these points here. So this point here is 2, 150, and this point here is 0, 0. And we could go m equals y2 take y1, which is 150, over 2 take away 0, which is 2, and that is 75 kilometers an hour. Now note that I could have done that anywhere along this line. So I could have taken a point there and a point there, and I still would have got 75 kilometers an hour because we're assuming that the car is traveling at a constant speed. Okay, so it just takes off and goes that speed all the way along. So any function that is linear will have a constant rate of change. This constant rate of change can be found by calculating the gradient. Okay, again, all of this is really, really important stuff when we're talking about calculus. Okay, 3 cars are driven over a 2-kilometer straight track. They all go from point A to point B. Each car travels with a constant speed. It is not a race, as the speed of car Y is twice that of car X. The speed of car Z is half that of car X. Illustrate this situation with a distance time graph. Assume that car X travels at 1 kilometer per minute. All right, so what have we got here? So the speed of car Y is twice that of car X. Let's do car X first of all. Okay, so we've got 2-kilometer racetrack. They go from point A to point B. All right, so if it's 1 kilometer per minute, then it's going to take them 2 minutes, or car X that is, going to take 2 minutes to travel 2 kilometers. All right, so here's car X's function. All right, so there's car X. Okay, now let's have a look at the speed of car Y is twice that of car X. Okay, so car Y will go 2 kilometers per min. Okay, so this is the rate that car X is traveling, and car Y is going to be twice that. So what it's going to do is it's going to do the 2 kilometers in 1 minute. All right, so I'm going to put another marker point here, the halfway mark, which is after 1 minute. It's going to travel 2 kilometers. So there is that car. So this is car Y. This is car X. All right, and the speed of car Z is half that of car X, i.e. it does 0.5 kilometers per min. Now what's going to happen with car Z is that it's going to travel 4 kilometers. There's 2, 4 will be somewhere there. It's going to travel 4 minutes rather, and do the 2 kilometers, okay, because it does half a kilometer per minute. So that's in 1 minute, half a kilometer, 2 minutes, 1 kilometer, and double that again. And we've got after 4 minutes, 2 kilometers. Okay, so there is car Z. All right, and there's our distance time graph. So there is time on the x-axis as usual and distance covered there. All right, what is the gradient of the following graph of Mr. L. Miller's typing speed with respect to time? All right, so let's calculate the gradient. And what we can do is grab 2 points. So I'm just going to grab 2 at random, completely at random here. So that's going to be 3, 60. And this is going to be 1, 20. So we're going to get the gradient. So m equals 60 take away 20, which is 40, 3 take away 1, which is 2, which is 20. Now, what does that gradient mean? So what does m equals 20 mean? Well, remember, it's a rate, okay? The gradient is a rate, and what this particular rate means is words typed per minute. Therefore, 20 words per minute. I don't know whether that's any good or not. 20 words per minute seems all right. Anyway, what is the gradient of the following graph indicating the exchange rate Mr. L. Miller will receive when he visits the USA at the end of the year? Hopefully he's going. All right. Anyway, so what we would do is m equals, so y2, so it's going to be 13359 over 1000, take away 4891 over 1000, all over 183 over 10, take away 67 over 10. All right, let's see what m is equal to. And we'll chuck divide in and then another divide to put my fractions in. 13359 over 1000, take away, shift divide, 4891 over 1000. Oh, another shift divide. 183 take away 67 all over 10. Probably should have done that with the numerator. And we get that m equals 0.73. Right, interpret it, i.e. what does it mean? Well, remember, that's a rate, okay? So what this means is for every, over here, if we have $5 Aussie, we're going to get, I don't know, it looks to be $3.50 US, okay? And what this means is for every for every $1 AUD, Mr. L. Miller will get 0.73 US dollars. Okay, so $1 Australian equals 0.73, and that is the exchange rate. And notice what it's called. It's a rate, exchange rate. All right, so there's the work for this particular exercise 16b. All right, so what we note here is that in 16c is that we're going to cover average rate of change. So many moving objects do not travel with a constant speed. In fact, it's really rare. Okay, it's really rare to see someone travel at a constant speed. Like if I drive to school, I'm very rarely doing a constant speed, particularly on our great Monash freeway. So consider the speed of a car or a bus when you're driving to school. It rarely stays still for long. It's always changing. It stops at the lights. It stops to pick up another passenger and another passenger and another passenger, etc., etc. So for a function that is nonlinear, the rate of change of the function varies and may in fact be different for every different point on the graph of the function. Does the quadratic right ever have the same rate of change? And girls, the answer is no. Okay, down here we've got a negative rate of change, negative, and the rate of change is varying because it's curved. Okay, so it's large here, so large negative, getting smaller, getting smaller, getting smaller, and it's got a zero rate of change here. This is called the turning point here. Okay, so it's got a zero rate of change here. The gradient at this point is actually zero. Then what happens is it's got a positive gradient all the way after that. So it starts getting bigger and bigger and bigger and bigger and bigger and just continues onwards. So no, it does not. Average rates of change are used to describe how one variable changes with respect to another over an interval such as time. So we're looking for, on average, between two particular points, what's happening to in this case here, the distance relative to time. So the graph of distance travelled meters against time in seconds for the motion of an object is shown. So the object starts up like this, okay, and goes like this. So you can see here we've got a large positive gradient getting smaller and smaller and smaller. Okay, so what this could be is, so the distance covered relative to time is high early on. So it might be like a car driving really quickly and then starting to slow down for the lights up ahead or something. So find the average speed of the object in meters per second over the interval from t equals 2 to t equals 12. So what I would do then is calculate the gradient of a straight line connecting these 2 points here. So remember, if I'm working out the average speed, which is a rate, it's a measure of distance covered relative to time, then all I'll do is I'll slam that into the gradient formula. M, so speed equals M equals, and then we'll do 30, take away 12, so y2 take y1, over 12 take 2, x2 take x1. And we're going to get 18 over 10, which is 1.8 meters per second on average between these 2 points. All right. Now, does it mean that it's 1.8 meters per second everywhere along here? Hell no. Okay, that means on average between these 2 points, our rate is 1.8 meters per second. But we can see here that at any individual point, it's going to be different than the other point I choose. The average rate of a function, there's a little bit of terminology you need to be comfortable with here. The line which passes through 2 points on a curve is called the secant. Okay, so a line which passes through 2 points on a curve is called the secant. Right, so let's just see if we can draw one up so that we can understand what this means. So there's a parabola or something resembling a parabola. Believe it or not, there's functions that look like this. A line which passes through 2 points on a curve is called a secant. So here's 2 points on the curve, and I want to draw a line that passes through it. Okay, so the line which passes through 2 points on a curve is called the secant. So this thing here, the line passing through the 2 points, that's called a secant. The line segment joining 2 points on a curve is called the chord. This thing here, okay, without the ends on it, that's called the chord. All right. So once we know that the average rate of change is the gradient of a line given or between two given points, and many of you use this formula here. So what I want you to do is note the subtle change moving forward. It's crucial that you, before you move any further, you understand what this looks like in function notation. So if I've got f of x equals 3x squared, and I want to find the average rate of change of f of x over the domain 2 to 6, okay, so here is 3x squared, and here is 2, and here is 6. So these points here, I want to find the average rate of change, so the gradient of that straight line. What are the coordinates of the endpoints? Well, I've got 2, comma, and then this y value of 2 banged into the function is 212. And I've got 6, comma, and 6 banged into the function is 6, 108. Now, I think you'll agree that the endpoints could also be listed as follows, which is 2, comma, and this is where the y value goes, and y is a function of x. All right, so we can put down, instead of writing 12, we can write down f of 2. Okay, so that can be just the y value there, which is f of 2, and the same goes here. And then if we were to find the average rate of change, we would just go, all right, it's the change in y value, so f of 6 take away f of 2, y2 take y1, and 6 take 2. So what we can do is use function notation to write that down. It's also going to be something really handy to do is define the function. So define f of x equals 3x squared, and then you can quickly run the gradient formula. This is something I do all the time for the 3-4 methods course. Just do f of 6, take away f of 2, all over 4, and we get our gradient between 2 and 6. All right, so I know that this may not seem like anything great to look at it like this. Okay, why use function notation? Why does it matter? But it will be important when we hit chapter 17. So more generally, the average rate of change of y with respect to the x over the interval AB is the gradient of the line through A f of A, and B, f of B, secant AB, right? And that is that we do f of B take away f of A over B take A. There we go, find the average rate of change of the function with the rule that as x changes from 1 to 5. So we're going to go average rate, or m, the gradient, is equal to f of 5 take away f of 1 over 5 take 1, which is 4. And that is going to be, and I really can't be bothered doing the execution of this, so I'm going to do it on the calculator. Find my mouse first. Define f of x equals x squared, take away 2x plus 5, shift divide, and we've got f of 5, take away f of 1, all over 4. And funnily enough, it is 4. All right, so that's our average rate of change is 4, and because there's no context of what y and x are, we don't have a unit on that. All right, the air temperature T at a weather station on a particular evening is modeled by the equation F of T equals this, where T is the time after 6 p.m. Find the temperature at 6 p.m. So let's use a little bit of function notation. That's F of 0, the initial temperature. So that's going to be 600. Again, let's use a calculator for this one. So I'm going to define the function f of x equals shift divide 600 over x squared plus 2x plus 30. All right, so f of 0 is equal to 20. 20 degrees Celsius, I presume. Yep, T degrees Celsius. Find the temperature at midnight. So we're doing time after 6 p.m. So midnight is 6 hours later. So we're going to do f of 6 equals, let's do that, f of 6, which is 7.692 ... degrees Celsius. Find the average rate of change in the air temperature from 6 p.m. until midnight. Now note that f of 0 is 20, f of 6 is 7.6. So what's happening here is that it's gone down from 20 to 8 degrees. And notice that that's going to be a negative gradient. So the average rate of change here is going to be negative. So the average rate equals f of 0, take away f of 6, all over 0 take 6 is negative 6. I usually do that the other way around. F of 6 take away f of 0, but it doesn't really matter what way you do it. So let's go shift divide. F of 0 take away f of 6, all over 0 take 6, which is negative 6. And we've got that negative 2.051 dot dot dot. And now we can interpret this rate has got context. Okay, so there would be suggested rounding here, but we're going to say that's that value there, and it's degrees. So degrees per hour. That's what it's changing by. So it starts at 20, and every hour it decreases by 2 degrees Celsius. And here is the same problem or the same method on CAS. I have to admit, for this year, we usually do Chapter 16 a little bit differently, but requires a fair bit of class time to do that, and you need to be there face to face. So I've actually pinched these notes from back in my Colesta days, and this is the calculator that Colesta uses. It's the TI Inspire. We use the Casio, so the output or the look of it looks different, but it's the same thing. Just quietly, the Casio is much better. My strong preference. So this is the method I use to get the average rate of change of the boat over an interval 2.3 to 4.8, where it sets out to sea from a jetty. Right, and so what we note here is we did f of 4.8, take away f of 2.3 over 4.8, 2.8, 2.5, and we got 10.4493 dot 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 dot. Now, what does that represent? Sets out its distance in meters from the jetty after T hours is given by this. So that's distance over time. So that is going to be meters per hour. So it does, it can't be right, 10 meters per hour. A small boat sets out to sea away from a jetty. Its distance in meters from the jetty after T hours is given by this. All right. It's not going very fast, but it's suggesting that every hour after 2.3, for every increase of 1 hour, it's going a further 10 meters out to sea. What is it, drifting? Anyway, all right, well, it's allowed to be what it's allowed to be. Right, and finally, what we'll do is we'll finish up with instantaneous rate of change, okay? So we've been investigating the average rate of change of a function over a stated interval. So we've been like going, right, between there and there. With the exception of linear functions, the average rate of change over an interval varies. So if you take there and there, or there and there, there and there, what we're going to get is a different rate depending on where we do it. Now, wouldn't it be interesting, well, I think so, to find the rate of change at any instant? That is, that if I was given a graph, I could find the exact rate of change there, or there, or there, or there. Not this average rate of change business, all right, that I can find the instantaneous rate of change. So the instantaneous rate of change gives us a much more accurate picture of how the gradient of a function is changing at any given point in time. All right, so what is this? We're going to talk about now a tangent line at a point. A tangent line is a line which has the same slope as the graph at a particular point. All right, so I'll open up that link now. All right, so what here we can see in this GeoGebra app here is that this blue line here, that's the function. That's f of x equals x take 3, all cubed plus 2. So it's an inflected cubic. This green line here is the tangent to the curve. All right, and this red line here is the secant, okay, going through point A and point B. Now what happens is if I bring this point closer to point A, what we'll get is a line that also is the same as this tangent line here. So this tangent line here basically runs along here, nicks the function, and keeps going. And at this point here, the tangent line has got the same gradient as the curve at this point here. So what's going to happen? Watch what happens to this red line as I bring this point B closer in. Here it comes. Here it comes. Ooh, I wonder what's going to happen. I wonder what's going to happen. Okay, so at the point exactly, what we find here is that the line that I've just done, the line joining a point A and a point B here, almost on top of each other, is exactly the same as the tangent line. Okay, so what we do here by doing this process here, so we bring this second point in really close to the first point, what happens is we get a gradient measure that's the same as the gradient of the tangent at that point in time. All right, let's just see how this works. So notice that when point B is moved closer and closer to point A, the tangent line becomes similar, the same. So here's a thought. If we want to get an idea of the rate of change or gradient of a tangent at any given point on a function, use that point and a point extremely close to it to get a good approximation. All right, that's what we're going to do. So our first point is going to be the point where we want to get the instantaneous rate of change. And the second point is just going to be excruciatingly, extremely close to it. So here's an example of this happening. Estimate the instantaneous rate of change of y with respect to x at the point 2, 9 on the curve f of x equals x cubed plus 1. So what we want to know is x cubed plus 1 is this graph here. We want to know the rate of change, the instantaneous rate of change at 2, 9. So what would happen is that a tangent would run along here, and that tangent's going to have a gradient, m equals. The gradient of that tangent will be the instantaneous rate of change of the function at that point in time. It'll tell us exactly what's going on. How are we going to get it? Well, what we're going to do is use 2 points. Our first point is going to be 2, 9, of course, because that's where we want to get the rate of change or the gradient. And then we're going to use a second point, which is 2.01, comma, f of 2.01. That is, I'm going to choose some second point that's extremely close to the first point, 2.01. Right, so let's grab it. So I'm going to jump on my calculator because you don't want to be subbing in 2.01 into this function. So shift and divide to insert the fraction template. And we're going to go, well, first of all, we've got to define the function. So f of x equals x cubed plus 1. This is really important that you do the function definition first. F of 2.01, take away f of 2 over 2.01, take away 2, or just 0.1. And there it is. So estimate it at x equals 2, the instantaneous rate of change is around or about 12.0601. That's my guess. And what we can do is actually sharpen up the approximation. I can get even closer by adding another couple of zeros there. And this is going to get me a better approximation because it's even closer. The 12.00060001. All right, I can get even closer. And the difference in the points can get closer and closer and closer. So what I'm going to suggest to you is that the actual instantaneous rate of change is actually, I think I just put too many zeros in, is actually 12. But this gets us a good approximation of the instantaneous rate of change, 12.06, and I choose a point 2 and a point extremely close to it. So that's how I do it on the calculator. So consider the curve y equals 2 to the x. Using the secant through the points where x is equal to 3 and a point extremely close, 3.1, estimate the instantaneous rate of change. Right, so again, what we're doing, if you want to picture it, is we've got a function y equals 2 to the x. And we want to know what is going on at x is equal to 3. So we want to get the gradient of the tangent at that point. We want the gradient of this line here. So what we do is we basically choose that point. Okay, so we're going to go and start with x is equal to 3 and y at that point, and another point extremely close to it, which is 3.1, so really close to it. We're going to get the gradient of a line joining those 2 points. So 3.1, comma, f of 3.1. So we bang it into the calculator. First of all, we're going to define the function. So define f of x equals 2 to the x. And we're going to go shift and divide f of, what are we doing? F of 3.1, take away f of 3 all over 3.1, take away 3. And we get an instantaneous rate of change, or a guess at the instantaneous rate of change, the gradient of the secant, or the gradient of a line joining the points 3 and 3.1 of 5.74. So we're going to say, so m equals, in this case, 5.7418, dot, 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 dot. And what we can do is we can do better than that. So instead of choosing the point x equals 3 and 3.1, let's get even closer, 3.001. So all I do is I just modify this, chuck another couple of zeros in and another couple of zeros in, and we get a better approximation. So in this case here, it's m equals, the gradient at that point equals 5.547 dot, 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 dot. All right, and on to then 16D to answer those questions. So hopefully you've been able to keep up with the conversation about gradients and instantaneous rate of change, average rate of change, and constant rate of change. All of those are really important when we start to work on calculus.